This is what our strips look like when enlarged. This is the recoil nucleus that moves here. Signals start here, and we decide whether we want to separate recoil nuclei from all other reaction products, which are also undergoing alpha decay, but are not genetically related to what we are interested in observing. In order to focus only on the recoil nuclei and its alpha decays, we can restrict our viewpoint to just 2 millimeters. The second indication will be that all of these successive alpha decays in the strip should end in spontaneous fission with an energy of 230 megaelectron volt. This is what the counter looks like with the start-stop detectors drawn here. And then there is the detector, which is shaped like a strip, and this is the container, which also has detectors on the sides, in order to collect products that fly in opposite directions. It looks good, even if I say so myself. But in fact, all this needs to be calibrated, because along the way, when this recoil nucleus moves forward, it passes through the gas and it loses energy. When it passes the counter, it also loses energy. Then it enters the detector, which has a dead layer and loses more energy before stopping. Firstly, it is necessary to correctly reconstruct and visualize the energy losses of the recoil nucleus itself. Secondly, it is necessary to envision that if an alpha particle flies forward, it gives all of its energy, and if it flies back, the problem begins again, because it passes the so-called dead layer, then flies into a vacuum before encountering the second dead layer, and here it expends the remainder of its energy. Therefore, in order to collect this energy, we need to take the energy from the alpha decays and add this energy to it. This also applies to the fragment which flew back. It turns out that the initial energy here was 41.5 megaelectron volt, but in fact, this detector registers the recoil nucleus with an energy of only 15 megaelectron volt, due to the fact that there are these losses that must be accounted for. This process concludes in 1 microsecond. Here the same thing. It's necessary to determine these deltas, which are losses in the dead layers of the detector. It is necessary to determine the loss of fragments in the dead layers of the detector. In fact, it turns out that what we are seeing is 195 megaelectron volt and not 230, but we have to restore 230 megaelectron volt from 195. It is better to do this under the same conditions as in the experiment. To our great delight, such conditions arise if lead is used instead of uranium, plutonium, or curium. Lead and calcium-48 provide element 102, which can undergo fission and which can undergo alpha decay. This is a well-known element, and all of its types of decay and energy levels have been recorded in literature. But we will try to obtain it in our system. And when we do so, we will calibrate all our detectors accordingly. The yield of this reaction is quite large. You can get about 1 decay per minute. So if you spend a few hours, you can get an accurate overview of our entire installation. Now, all detectors are calibrated according to this method, using element 102, and lead is being irradiated with calcium-48 worldwide. According to literature, the graph depicting the recoil nuclei of nobelium looks like this, but we obtained these results with our detector. You can clearly see the difference. Here we have a graph depicting fission fragments where the first value was taken from literature at 194.3 megaelectron volt, and we obtained 174 megaelectron volt. Here we measure 210 megaelectron volt, but in fact it should be 230 megaelectron volt. Finally, a depiction of alpha particles. We know the number of alpha decays per unit of time. And most importantly, we define this stripe, the position deviation, which, according to data, is 0.65 millimeters. So, what is the result? We have the transmission of the nuclei we are interested in, 35 to 40%, and we suppress the nuclei we are not interested in by 4 to 7 orders of magnitude in the separator. We almost completely suppress the beam, and the registration efficiency of the alpha particle was 87% in this container. The efficiency of spontaneous fission for a single fragment was 100%, and for 2 fragments, it was 40%. The flight time from here to here is 1 microsecond, which is the minimum time. It's good that we have a minimum time in place. But what if they live so long that this minimum time is not needed? This is an uncharted area. They can live for a second, they can live for an hour, they can live for a day. What should be done in this situation? My colleagues have invented a very good method for dealing with that issue, and I am very satisfied with it. We will look at it next.